the actual task of showing how symmetry helps, let's just do one more exercise and let's look at that. So let's look at the BSC. So for the BC, it's again, we have again symmetry, channel is symmetric, code is linear, hence we can again do the all zero code word assumption. So we're just looking at the error pattern. So again, we do now an error will be a 1, a 0 will be it's correct. And we're just looking at the error patterns. We assume that so whatever I'm drawing is, again, the omegas will be the error pattern. So this will be the set of decodable error patterns. So these are now the decodable ones. So before we had the ones where I make errors, but so this now means the mu of omega is now 1 minus the block error probability, okay? But it doesn't matter because, this is, it's just 1 minus, okay? It doesn't matter if I have a sharp threshold. And so now this set is easy to see that this set is monotonically decreasing. So let's just see what decoding here means. So decoding really, right, means that I have my all zero code word that I sent. And so this is the zero word. And now I have some omega. And this omega has a certain number of bit flips. So there's a certain number of errors here. And so what I'm doing, decoding means I'm looking for that word that's the closest one, and then I'm breaking ties in some ways as I have to, okay? So if there's any other code word, then this other code, if I have any other code word, then this code word might have some particular overlap, maybe, okay? So there might be a certain number of ones, and then it might have a certain number of ones here. So let's maybe this overlap be delta, and maybe this overall thing here be the weight be b of this word, okay? So if I get this pattern, I'm just looking for that word that has the smallest distance. So for example, the word from here to the zero word, right, will have distance a, right? There are a ones here, so it has distance a, right? And so let's assume, so to be in set, to be successful, to be in that set, it must be that this pattern has no neighbors that are closer than a from here, right? So let's just check. So what would this mean for the overlap? What is the distance from this to this, right? So the distance from here to here is what, right? It's a plus b minus 2 times the delta, right? Because I have, it will differ here. It will differ here, but I twice have counted the overlap, which I shouldn't because it's 0 again, right? And so, so this here, if that's larger, then this be better larger than a, right? So that I don't confuse it with the a, right, for this overlap. So what does it mean now for a point to be on the boundary, right? For a point to be a boundary, it must still be this, but there must be a way to flip something, right, from 0 to 1 now, such that when I flip it, that then suddenly something else is closer, right? So for example, let's assume that this is equal to a plus 1, right, this distance here. Then let's have a look, right? So if I flipped, for example, now, so for example, if I added now an error here, right? So if I took now this and I added an error 1 here, right? Then this distance from here to here would go from a to a plus 1. But this distance from here to here would go to a because it would be 1 less, okay? And suddenly this would be larger. Is that clear, right? So the question is, so in order for this to be in a boundary, it must be that this is, is just as close to this, just about as close to the 0 as it is to some other code word, right? Just with one difference. And if that happens, the question is, by how many ways can I add now a 1, right? And so this happens in all these guys here, right? Whenever I have anything here, right? Whenever I flip one of these, so any of these positions here, when I flip them, I will be closer now to the C than I will be to this, okay? But, let's just check here, right? So I have here I can cancel this, right? So I have that the delta will be, let's see, what do I want to say? So what do I want? I have that, yeah, the delta will be roughly, so, delta will be roughly b over 2, right? But also what's left here, right, will be roughly b over 2. So what must happen is that this overlap and what sticks out must be roughly half the code word thing, right? And in particular, will be at least half the code word thing here. But every code word must have minimum distance at least dh, right, the minimum weight. And half of these positions, when I flip them, it will go from the code word to, will go to outside. And hence, I'll get exactly the dh over 2 here, okay? So it's slightly worse than for the erasure channel, but at least the scaling is the same, right? It's just different in the constants. Okay, so far so good. So let's repeat. Any code that has a good minimum distance has a sharp transition for its block map threshold under maximum likelihood decoding, and that's true for the BEC or BSC, and people have also looked at the Gaussian, but I haven't mentioned this. But unfortunately, for proving that a code achieves capacity, the block and the bitmap threshold, so even, remember, if we can prove that the bitmap threshold jumps, then we show that it's capacity. If we can show that the block map threshold jumps, that's nice, but that's not, that's not what shows us capacity. So the question is now that I want to now look at is what happens if we're looking at the bitmap threshold. And so in particular, we're going to look at Reed-Muller codes. And actually, it turns out that even though we look at Reed-Muller codes, I don't even tell you how Reed-Muller codes are defined, because we actually don't need it, okay? The only thing that we'll need is that these codes have a high degree of symmetry, so whatever is valid, what I say, has just to do with the fact that these codes are highly symmetric, and nothing else with the particular structure of Reed-Muller codes. And so there were at least, two groups, so this is, so this is Srinivas Kudikar, Marco Mondelli, Aaron Shashoglu, and then there's another group with Santosh Kumar, and this you can hardly recognize, is Henry Pfister, okay? And so there were basically two independent works we were all done when we were essentially at the Simon Center, and then we realized this is essentially the same thing, and we put it together. So I'll just give you now the presentation of the joint idea, and there's been much follow-up work, so I'm just giving you the basic flavor. Okay, so as I said, the motivation for looking at Reed-Muller codes is that empirically they do quite well, and they go back quite some time. It was Reed who had actually kind of discovered these codes, and then Muller who gave some originally majority decoding algorithm to decode these codes, not in the fashion, not in maximum likelihood fashion. And so these have been around since the mid-50s and were a staple of coding theory. And if you look at standard books like Neil Sloan's book, the whole chapter's dedicated to the beautiful properties of Reed-Muller codes. They're the answer to pretty much any question you ever ask, okay? It's always Reed-Muller code somehow, okay? Good. And there was actually a lot of follow-up work by Ilya Duma, who came like epsilon close to discovering polar codes, because they're very related to these Reed-Muller codes. He did pretty much anything, the successive decoding, but it just did it slightly different, and so it just somehow didn't click, but he should be given a lot of credit for looking at various aspects of decoding of Reed-Muller codes and something that looked almost like polar codes. Good. So now, the only description that I will give you about Reed-Muller codes is one that relates it to polar codes. And so for polar codes, you start with this matrix here, the generator matrix 1, 0, 1, 1. And now you just do the Kronecker product. So you replace every 1 with this matrix itself, and every 0 with just a 2 by 2 0 matrix, okay? So if you start, with whatever, you start with 1, 0, 1, 1, and then this is just for 2 by 2, and then if you want the 4 by 4, you replace this with 1, 1, 0, 0, 0, 0, and then you do the same thing. Okay, so now you have a 4 by 4 matrix, and again, you replace every 1 by again this small matrix, and so this way you get powers of 2, you get 2 to the n by 2 to the n matrices. And so now these are basically the generator matrices of the code, except that this is, of course, n by, 2n by 2n matrices. And so you don't want the rate 1 code. And so the only difference between polar and Reed-Muller codes is which of these rows you pick. Okay? And so Reed-Muller codes, the thing is very easy. You just give me the rate, and then you pick the ones that have highest weight. Okay? You just pick the ones that have the most ones in there. You just sort them. And you take all the generators that have, for example, the all 1 is in there. So that will be in every code. That's non-trivial. And then you just sort them by weight. And a nice property of Reed-Muller codes, which is in general, of course, absolutely not true, is that the minimum weight of the code will be equal to the minimum weight of the generator that you include. Okay? In general, of course, if we give you a generator matrix, and these have certain weights, right? You know nothing about the weight of the code. You have to look at all 2 to the, 2 to the NR combinations to see. But due to the structure, okay, it turns out that the minimum weight of this code is exactly to the minimum weight of any of the generators that you include, okay, which is a very strong property. Versus for polar codes, we didn't talk about it. But for polar codes, the rule is simply different, is that you have to have this, for every row, you can compute some reliability, and there's kind of like a dense evolution. And this is what this picture is to show. So you have a certain decoding order. And according to this order, you can compute to every position. So each of these bits corresponds essentially to one of these rows that I showed you beforehand. And then to each of them, you can associate a certain reliability. And you pick the ones that are most reliable. Okay, so it's just a different rule. And we understand actually very well what the connection is. So how many of these rows are in both? Okay, so that's exactly equal to 1 minus the capacity, or 1 minus the rate. Okay, so if you pick a Reed-Muller code of rate R and a polar code of rate R, and you look at long codes, you know exactly what's the intersection of the rows that you have, okay, the number of intersections you have. We understand this very well, but then there's some that are just, there's some generators that are only in the polar code, but not in the Reed-Muller, and there's some in the Reed-Muller and not in the polar, and then there's a common core in there that's in both. Okay, so now, why, as I said before, and why are we interested in these Reed-Muller codes? So this is just a simulation, and just for a particular one, and I showed it already in the very first hour, but let's maybe revisit this. This is just some particular length 1,000, rate a half, and this is for the binary ratio channel, and this is the block error probability for the polar code. If you can do block map, so maximum a posteriori decoding. And so, as I said, they share some of the rows, but some rows are different. So you can think of kind of like an interpolation between the two, where you slowly, as a function, alpha goes from 0 to 1, where alpha, let's say 0 is a polar code, alpha is 1 is a Reed-Muller code, and you kind of exchange slowly rows. The rows that are not common, you slowly, move ones out and the other ones in, okay, in some particular way. And if you do that, you will see that as you go along, okay, you do better and better. And so now you actually achieve the Reed-Muller code. And actually this black line turns out for this particular case, the finite length bound. So at least for this case, it looks like that this is smack on the best thing that you could actually do, okay, according to information theoretic considerations. So we don't know yet exactly if polar codes exactly achieve the optimum exponent, but there's, at least numerically, it looks actually pretty promising. Good. Okay, so as I said, what we would like to do is first do the even achieved capacity, and that's what I'm going to talk about today. Second, what is the scaling? Hopefully we can show that the scaling is also essentially optimal. And then third, and that's the biggest open question, is how do you efficiently decode them? Okay, all of this is if you could decode them optimally, right? And we don't know an algorithm currently. But also, I think there's the following twist. Often in coding theory, progress didn't come by solving the difficult problem, okay? But we just got better and better at finding backdoors, okay? So initially, right, Hamming told us find an optimum, optimum packing. And then a lot of people scratched their heads, and then some progress was made, but it's very difficult. And the progress didn't come by someone solving the optimum packing, but by someone finding a different way. And so also here, you should think about that And this, this repeats over and over again, and I think that's a general lesson, I guess that every researcher does. If you can't solve a problem, you just change it, right? And then you solve that problem, and then, often that's valuable. And so in particular here, we are not interested necessarily in decoding this code. We're not necessarily interested even in what the complexity is as a function of n, because the only reason we need these codes is for very short block lengths. I'm talking about 500 and 1,000, right? And we're not interested in if n goes to infinity what the complexity is, because for those things anyway we have codes that do excellent and you can hardly improve upon. But we are interested in, can you with current hardware find an algorithm that something like length 1,000, a reasonable rate, can decode, okay? And perhaps it's even exponential, but the exponents and so on are so small that for length 1,000, that's perfectly doable, okay? And that should change a little bit our mindset, because we're not necessarily looking for an n or n log n algorithm, right? And so, keep that in mind. Good. So, okay. So we're interested in right now. We're just trying to see if these codes achieve capacity. What happens? I'm going backwards, forwards. Okay, so this is, as I said, this was like one of the open problems in assignments where several people were visiting. And there had been some progress made already beforehand, also recently, by Avi Wittgersen, Spilka, and Emmanuel Abe. And so these are computer sciences. So in computer science, you use codes for all kinds of other things, not just communication. And then very often you're not, we of course in communication, we're always interested in the rate being fixed somewhere bounded away from 0 and 1, and then n becoming large, etc. But in computer science, the scaling can often be very different, okay? So it might be interesting to look at codes that have rate going to 0 at a certain rate, or codes that have rate 1 minus something that goes to 0. And so they indeed, they indeed look for the BC and the BSC, and looked at certain regimes. For example, if the rate goes to 0, 1 for the BSC, they proved that indeed, now you have to even think about exactly what it means to achieve capacity if the rate goes to 0. So you have to have a proper definition. And for the BSC, if the rate goes to 0, yes, and BSC, if the rate goes to 1. But these are all very nice, and this was combinatorial by looking at weight distributions, similar to what I had proved before, and by finding better bounds. But these are all things for which, for communications, that's not the regime, of course, you're interested in, but it can be very valuable and interesting for different applications. Okay, so right now we are looking at the regime essentially fixed. The R can still go, so there's a certain regime where the R can go to 0 and to 1 at a certain gap, so these two are not completely independent as results, but we're looking right now, everything I tell you is where the rates are bounded away from 0 and 1, and it's slightly more subtle when the rates vanish, okay? So, and as I said, now, the idea will be very similar to what we had just looked at, but right now we need to look at the bit error probability. Sorry? Yeah, I guess these are Indian spices, yeah, I guess so. But when I made it, I had no, yeah, sorry, I had, well, maybe you like it, but I'd actually, at that point, I wasn't thinking actually of coming, I shouldn't say that, because, no, I did it specifically for coming here, okay? So anyway, so there are three, they're basically just three ingredients, and we have already talked about the last one, okay? And also the second one, but in a slightly, we need a slightly different version of it. So there's really only one ingredient that we haven't talked about at all, and that's this symmetry. So first of all, why can't we just use exactly what we have done right now? So if you're looking, for example, for the BSC, and you're looking at all the error patterns for which you can decode a bit or not, okay? Now it's slightly different, okay? So what you're interested in is not that there's a code word that's covered by the erasure pattern, but you're interested in that there's code word that's covered that has a 1 at the position that you're interested in, okay? So we're not just interested in, so for the block we were interested in, for the block error probability, we were interested in you cannot decode if you have a pattern and so if there was ever a code word C that was covered, right, then this means there was another code word here and you couldn't decode. But if we are now interested, for example, to see whether we can decode the first bit, right, then we can decode the first bit if and only if. So for example, if this was the only code word that was covered, you could still decode the first bit. Why? Because the only two code words that are compatible with it is the all 0 and this code word, but they both have 0 at the first position, okay? So it doesn't matter whether I know these two things. I know that there's a 0 and I'm done, okay? But if there was a code word, if there was a code word that had a 1 here at this position, right, then there's of course the 0 code word, and there's this code word, and there's an equal, because due to the linearity, there will be an equal number of code words that have a 0 at the position and equal number of code words that have a 1 at this position that are covered, and then I cannot decode this bit. So if you look at that thing to be your set, okay, then you can, it's again monotone, of course, right, because once you cannot decode and you add more things, you will still not be able to decode. But unfortunately, it turns out that for this set, remember what we had this delta, which was the minimum of all these h omega, right? These were the boundary points, and this was by how many neighbors they had, right? And we were interested in what's the smallest one that we had here, okay, that came in the theorem. And unfortunately, this is like 1 or something like that. It's a constant, okay? So there are some points, unfortunately, for which this is very small. So you can just not use, you cannot use this idea, okay? So, so there's a slightly different way to go about it. And so what we need here is a symmetry. And read-middle codes have, beside this description, about 20 other different descriptions, as evaluation codes, et cetera, et cetera. So they have very many descriptions. And so in particular, they have some very beautiful property that was discovered by these 3 researchers already. I think it was 70. I can't remember, I think late 70s or 80s. And so that's symmetry, okay? So let me just tell you what symmetry we mean. In particular, these codes are at least 2 transitive, and I'll tell you a little bit more. But let me first tell you what 1 transitive means. And it's very easy. So write down all the code words. So this is a very simple code that has only length 8. And I'm writing down all the code words here. And so now what I require for code to be 1 transitive is the idea is that I want no position to be any different from any other position. Okay, I want them to all behave the same way. And one way to formalize is the following, is that you give me any pair I and j, right? And so then there must exist a permutation of the basic components here, right? Such that this permutation maps I into j, right? So there's one condition that you have, okay? And then, so then what happens is that when I do this, so let's just see, for example, I want that the first column here gets mapped, the first position gets mapped into column 3, okay? And so then now there must exist a permutation that does that, okay? So this gets mapped into that. And the other ones, I don't ask what columns go, this must be just some permutation. But now what must happen is that if I look now at the rows after the permutation, as a set, it's identical to the set here, okay? That's not completely obvious because the rows have now been reordered, but there must now exist some permutation of the rows, right? And if I do this permutation, you see that these are identical, okay? So the code stays invariant so for any I and j, I must be able to map column I to column j, okay? And then there must exist a permutation such that if I apply the permutation to the whole code, the code stays invariant as a set under this permutation, right? So that's what's one transitive means. And then it's fairly clear what 2 transitive means, right? 2 transitive simply means that now I can ask you 2 requirements. And of course, I cannot ask that I goes to j and k goes to j, right? But as long as I do this, that these are compatible, right? So for example, I ask here that 1 goes to 3, and I ask that whatever 8 goes to 4. Okay, and so now there must exist a permutation, right? So this goes here, and again there must be now some things of the rows, and these 2 codes are, and the code stays invariant under this permutation. Okay, which are non. So it should have been that this column should have moved over there, and this column should have moved over here. All right? But I can choose any pair, as long as, of course, I cannot ask that the same thing goes to different places, or I cannot ask that two things go to the same place, right? I mean, it must be compatible. And I don't put any permutation on the rest. So I could also ask that, for example, one position stays constant, one column stays, for example, and then another one goes over here. Okay? So anything, any permutation that's consistent, any two conditions I can fulfill. Okay? But maybe I didn't quite understand, but I suspect I didn't quite understand, so we can do it afterwards, okay? Good. So now this is again, this is very similar to what we just talked about, but this is a slightly different version, okay? So what we had in what I said before was that we had a set. The set was monotone, and we had some condition on the boundary, on the boundary points, how many neighbors they had, okay? And it was important that every boundary point had a number of neighbors that was growing, right? And then we could say that things were fast. So here it's different. We're not asking for this thing, but we're asking the following. We're simply saying that if I have a set, and the set is monotone, and the set also has a symmetry, okay? Then again, the symmetry will also make sure that the transition goes fast. Okay, so let's just look. So this is a different condition, but this should look all now very familiar, right? So we have a subset of 0, 1, right? And this subset is again monotone. So this is exactly the same what I had pointed out before, right? So this is exactly the same, omega, and this set is monotone. So if something is if something is in the set, then if I flip an extra bit from 0 to 1, it's still in the set. Okay. So if by adding more ones, I'll just stay in the set. So for example, this one is monotone, right? So if I take this one and I flip this extra 0 to 1, then it's already in there, right? Or I flip from the extra 0 to 1, it's already in there. Okay, so that's fine. But let's see, for example, this one. This set would, I guess, if I took this out, then this set would no longer be monotone, right? Because if I flip that from 0 to 1, it would no longer be in there. Okay, but now I also want that the set is symmetric. And so, for example, imagine here, so again, this is exactly the same what we said before, and that is one transitive. Okay, so again, I want that this set is the same thing as we said, one transitivity beforehand. Okay, so I only ask for one transitivity of the set and not for two transitivity, and this will become clear in a point. So, for example, here, if I looked, for example, at a cyclic shift, okay, you can see that this set is symmetric. Okay, so we have again the omega. But now, instead of asking for the boundary points having lots of neighbors, we're asking simply that this set has a certain symmetry. Okay, so that's something, for example, wouldn't be symmetric. Now, this we have also already seen, right? So we have this set, we take this Bernoulli product measure, where associated to any element here, simply I have a parameter epsilon, e to the weight, times 1 minus to the n minus the weight, and the weight of, or the measure of the whole set is just the sum of the measures, and so that's the standard one that we had seen here. And again, a 1 will indicate for us an erasure, and a 0 will indicate for us that it's correct. Okay, it's the same mapping that we had beforehand. Good. So now, so there were these beautiful papers by Kalai, Friedgut, and Bourgain, and then there are many, many other follow-up papers by many, many combinations and other authors, okay, that I don't even try to summarize here. But these were the first people that had proofs of the form that monotone symmetric sets have sharp thresholds, okay? And we use this now for coding, but this has been used in computer science for many, many other applications, and is one of the staples, really, of theoretical computer science. And so, as we said before and already, so this will be a similar picture, right? So this is, for us, this will be the probability of decoding error, but for them, it's simply the probability of this set. And so it simply, again, means that this goes quickly from, the measure goes quickly from some delta to 1 minus delta. And so now here, before, and remember, we had here something like 1 over square root of d, okay? But so now, instead of 1 over square root d, the speed goes, because we have a different condition, this is replaced by 1 over log n, okay? So this one here is what we had before, and we had the log of 1 over delta beforehand, right? But this condition is now different, right? In the Seymour thing, we saw that this had to do with the square root of the minimum number of neighbors that you had, okay? Now we don't have this condition. Now we just have symmetry, and that's replaced by 1 over log n. Now, of course, you know, kind of this condition is perhaps weaker. And you know, remember, like in coding, the minimum distance could grow as large as this, as n, as linear n, and so we got something as good as 1 over square root of n, right? Versus here, if we're using something like this will only go like 1 over log of n, okay? So we'll be considerably weaker. There are slightly better versions. If you have more symmetry than this, okay, if you don't just have one transitivity, the more symmetry you have, the better. And so this could go as fast as 1 over log squared of n, okay? Which is already, I mean, it doesn't look like much, but it's already significantly better, but you're never gonna get like 1 over square root of n in here. Okay, so, so this is what we're gonna use, right? And so, as I said, this already mentioned before, and so these are, this is Seymour and this is Tillich that had these beautiful papers that I mentioned before, and with the 1 over square root of n. And so now, but also note that these kind of proofs, when they show a sharp threshold, that's just simply proof that there's a sharp threshold. Similar as you get, for example, when you use in probability Azuma's inequality, you get a concentration. But neither in Azuma nor here do you know what the value is that you concentrate around, right? It doesn't tell you anything about the mean. It doesn't tell you anything about where this threshold happens, right? We simply said that there was a fast jump, but this jump could have been anywhere, okay? So that's important to note. So this is a technique simply to show where that the threshold happens, but it doesn't show you where. Okay, and so now this is now easy for us, okay? So déjà vu, this should look similar, okay? It should look familiar. So these are now these area theorems. And so this is, of course, what we will use to pin down where the threshold happens, right? Once we know that there's a fast threshold and we know it's for the bit, right? At least for the BC, that's equal to the exit function. And we know that the exit function, this threshold, or this jump has to happen at where the area threshold is, right? It has to happen actually at the capacity. Okay, so I can actually, with this, I don't need to go over it because we know all this thing. And so, as I said, the original thing, this Stefan ten Brink, Gerhard Kramer, and Alex Ashikmin, that had the original version of the area theorem for the BC. Looked different from what I presented to you, and this is Cyril and Tom and Andrea for the way that I presented it to you. Okay, and so this we have also seen. Okay, now you can review. Okay, so anyway, okay, this is just the area theorem that I showed you beforehand. Good. So now, how do we put things together? Okay, so okay, so as we said, exactly as before, and so we have this set of erasure patterns that cause trouble for bit I, right? And so these are exactly the ones that have that erasure pattern where you cover a code word that has a 1 at the special position, and otherwise it's just covered. Okay, so these are the ones that cause trouble. And so those are the ones that I'll put in my set, okay, in my set I. And so this set now will depend on actually the position I, right? So the set of erasure patterns that cause trouble depends on which position I am looking at, right? So this depends on it. But you know, this won't cause a trouble. Why? Because we know that due to the symmetry of the code, all the exit functions for each position, just because of the one transitivity, they are the same. Okay? So we might as well just thinking of one. It doesn't matter which one. But since the code has the one transitivity, this will be all the same. Okay? So it won't be a problem. Okay, and so that's exactly what I want to show. So if I have a pattern here, right, and these are the erasures, and so I'm looking at this special position here, it must be that all the other ones are covered, and this thing must be 1 at this particular position. Okay, then only then will this cause trouble, right? So then I won't be able to tell. There will be an equal number of code words that have a 1 at this special position and are compatible, then that have a 0 at this special position and are compatible, okay? And so then, of course, my exit function or my error probability will be exactly equal to the measure of that set, so it's perfectly set up for setup. And so now we just need to check a few things. We need to check monotonicity, right? Remember that the set had to be monotone, but that's fairly clear, right? So I'm just looking at the set now, other than this one special position, and in the rest it's of course monotone. As soon as there's something in there that has a 1 at this special position, if I add some extra 1s, there might be more code words that have a 1 there, but it will still contain 1, so it's clearly monotone. Okay, so monotonicity is completely obvious, and we don't really need to do this. But remember, we also want that this set here, the omega I, must be symmetric, right? And so now we'll see why we need a two transitivity for the code. Why? Even though we only needed a 1 transitivity for the set. Why? Because when I want to define this symmetry, this one special position here, I, that needs to stay fixed. Okay, so I need to define now a permutation that keeps the position I fixed. And then for the rest, I still want to show that the rest is symmetric, right? And so hence the 2 transitivity of the code will give me the 1 transitivity of the set omega I, okay? Because I just need to fix this position I needs to be fixed on the permutation, and the rest, and now and maybe I want to map this to this here, okay? And that's my symmetry that I have. Okay, so it's symmetric, so these are just in formulae that it's symmetric. Yeah, and so then we said already that these HIs, that all these exit curves will be the same because the code is transitive. So I just might as well look at one curve and I don't need to look at the average, because remember it was the average that fulfilled the area theorem and not each individual curves, but since they're all the same, each individual curve will fulfill the exit function. Okay, and so now we are basically done, right? We know that putting these things together, we know that one individual exit curve has now a sharp transition, right? And the width will be 1 over log n, right, in this transition. And so as n grows, this will give us a sharp threshold. But now we don't know yet at that point what the transition is, but now we invoke the area theorem. We know that this transition is for the exit function, so hence this must exactly happen where this is the rate of the code. And, but if that's where the rate of the code is, then the critical thing is 1 minus r, and that's exactly, of course, the capacity, okay? And that shows why for the binary ratio channel that is indeed the capacity, that these codes fulfill the capacity. So all we had used symmetry, okay? So any code that's symmetric. And so for the Miller code, you can do a little bit better. So the code, the symmetry group of this code is known and was defined by these Peterson and Weldon authors. And so actually it's the following, that if the code has length 2 to the n, then every position can be indexed by a vector or by a binary vector of length small n, right? So let's assume you go from so you have n bits that indicate all so the capital N, the block length, is 2 to the small n, and then all the positions from 0 to capital N minus 1 can just, I can put this in one-to-one relationship to all the vectors of small length n, right, from 0 to 1, 1, from 0 to 1, 1, 1, okay? So this is, of course, 0 here, and this is n minus 1. And so if you think of this, then the permutations can be all permutations that can be described in the form like this. So it's like some generalized linear group. So you take a matrix here that's small n by n, some invertible matrix, binary matrix. And so any permutation that you can describe by taking the indices here, okay, for a fixed matrix M and for a fixed shift G. Okay, so that describes a permutation. For every such matrix and for every step G, this describes a permutation. And any such permutation that's describable in this form will be in the symmetry group of the code. Okay, and so that's actually slightly more than just 2 transitive. And so because this code is slightly more than 2 transitive, one can actually show that this transition is not just of order 1 over log n, but a little bit better than that. Okay. Because in this theorem, it all depends on how big basically the size of the symmetry group is of this set. And if it's more than just 1 transitive, then you get better mixing and you get a better performance. Okay, so yeah, so there's still the question now, block versus bit. I think I'll talk about it tomorrow. Okay, I'll quit early today. Is it okay if I quit slightly early? Okay, so I'll do this story tomorrow. So there's still a question right now. So what does this show? It shows that, you know, where the bit error probably that goes fast, but it could be that, of course, the block error could jump somewhere else, okay? And so we still need to tie the bit to the block together. So if I'm only interested in bit error probability for my performance, that's fine, but what is if I'm interested in block? Does it also achieve, in terms of the block error probability, the threshold? And so there are two ways of doing it, and I'll show you this tomorrow together with a better scaling. And there are two ways of doing this. And then, as I said, it could be other codes, like some special version of BCH codes also have this property, and so they also achieve capacity. And Henry and Santosh have looked at many, many other versions of codes, and so there are many other ones that fall into that. And as I said, you know, we were cautiously optimistic, but I'll tell you tomorrow why we are mostly cautious now, okay? Or at least we don't know, but it's a challenge for you to try to find the missing proof, okay? And that's the end for today. Thank you very much.